mathematical tool, that is a Laplace transform. I guess some of you are very much familiar with the concept of Laplace transform. So I shall be giving you a very brief overview of this Laplace transform. Okay, and what is the functionality of the Laplace transform, or where we can find the use of the Laplace transform. Now, if I try to summarize Laplace transform, the Laplace transform can be termed as a method, that is an operational method, which can be used for solving linear differential equation with great ease. How? Because by the use of Laplace transform, we know we can convert any differential equation into algebraic equation. Not only that, the Laplace transform also finds its application in various analysis in signals as well as system analysis, especially because of the fact that it can convert many common functions such as sinusoidal function, damped sinusoidal function, or exponential function into functions of complex variable s, which is in algebraic in nature. So it converts sinusoidal, damped sinusoidal, or exponential functions in type to algebraic function of the complex variable s. Similarly, differentiation, we know it converts in a differentiation to an algebraic function or algebraic operation. And integration can be also replaced by an algebraic operation in Laplace transform domain, that is from time domain to frequency domain. Therefore, once you have converted from system theory point of view, once you have converted a linear differential equation into an algebraic equation in the complex variable s, then you can solve for the differential equation to find out the dependent variable in s domain. Now, if you want to come back to the time domain, then we normally use what is called the inverse Laplace transform. Okay, so in this way, what happens? Given a differential equation, we know if it's a higher order differential equation, it requires a number of integrations depending upon the order of the differential equation. And the integrated integration always involves multiple stages to get the final answer, right? So in Laplace transform, however, we can get the final answer in a one go. There's no need to find out the particular integral or things like that. So you can find out the answer to a differential equation in one go just by some algebraic operation and Laplace transform and inverse Laplace transform. So you should be aware of this Laplace transform and inverse Laplace transform. Okay. So let us see what is meant by Laplace transform. Okay, why or how we can use the concept of Laplace transform in reality. So we need to first understand what is Laplace transformation. So we have to define what is Laplace transformation. So I think you know all these things. Just I will recap it very quickly. So given ft, which is a function of time, such that we shall consider this ft equal to 0 for all t less than 0. That is, the function is only defined in the range from t greater than equal to 0. And in Laplace domain, we have a frequency s, which is the complex frequency, which you can represent as having a real part and an imaginary part. Now we define an operational symbol L, which indicates operation, that is Laplace transform of say any ft, right? And therefore we can write by definition that fs is Laplace transform of ft. The thing that I have to remember or I have to recollect that whenever I'm doing this is normal procedure or normal decorum. So a time function will be depicted and declared by a small function, small letter, and its Laplace domain representation will be in capital F, small f t, capital Fs. And how it is defined? It is defined as per our definition, 0 to infinity e to the ft st dt, right? So this is how we can obtain the Laplace transform, and this is called, since we are only considering from 0 to infinity, one-sided Laplace transform. Okay, so LT. And because of our definition that our signal is only valid for t greater than equal to 0, we are defining our one-sided Laplace transform as this. Once you get Fs, you can find out Ft by carrying out an inverse Laplace transform over Fs, which is again defined as for all t greater than equal to 0. Now, what is this C? C is called the abscissa of convergence, and it is a real constant, and it is chosen larger than the real part of all the singular points of Fs. Singular point means at those points where Fs ceases to exist. Okay. Now, as you can see, the finding out inverse Laplace transform given in Fs is not that easy. It is very cumbersome exercise. So what we will do, we'll use in this regard a standard table that is available for common functions. The standard table is available where for those functions the corresponding inverse Laplace transform is always defined. So we'll rather use those table to obtain the inverse Laplace transform. So our objective will be to reorient or reorganize the function fs in such a way that it can be thought of a augmentation or combination of such common functions, so that you can use the inverse Laplace transform table to obtain the corresponding functions in time domain. Okay, so this is starting with the basic definition of Laplace transform, and now we'll see how we can use this technique to obtain the Laplace transform of different common functions, right? Let's quickly recap those. So first, let us take a step function. How is a step function defined? If t is equal to 0 for all t less than 0, equal to say a for all t greater than 0 and equal to 0. When a is constant, so Laplace transform of ft will be 0 to infinity, and from this range it is a e to the power minus st dt. So it will come out like a by s, right? And for unit step response, it will be 1 by s. For unit step function, it will be 1 by s. Next, the common functions that you normally use. Ramp function. How is the ramp function defined? Ramp function is defined as ft equal to 0 for all t less than 0 and equal to say a t for all t greater than equal to 0. Then you can find out Laplace of f t as 0 to infinity a t e to the power minus st dt. So this will be like, since there are two parts of the integration over here, you can just simply associate this as at st by s with a minus sign for this exponential part from 0 to infinity minus to infinity a e to the power, sorry, minus st by minus s dt. So if you take both the sides similarly, so from that you get and from this side you'll get, this time will be, see, for infinity it is 0, for 0 it is infinity, so it will be simply a by s 0 to infinity e to the power minus st dt. Since it's only e to the minus st dt, it will be a by s square. Okay, so for ramp function comes out to be a by sorry s square. Now another important function that we normally encounter is, say, an exponential function. Suppose we have an exponential function like f t equal to 0 for all t less than 0 is equal to a e to the power minus alpha t for all t greater than equal to 0. So what is the Laplace transform? F t will be from 0 to infinity a e to the power minus alpha t, so a to the power st dt, that is infinity e to the power, a is common, minus of alpha plus st dt. So it will simply come out to be a upon s plus alpha. So whenever you have a exponential function e to the power minus alpha t, just like had that been a, I could have got a by s. Now due to this e to the power minus alpha t, what I will get, a by s plus alpha. Okay. Now using this technique, we can now find out the Laplace transform of a sinusoidal function. How? Each and every time you have to declare this thing, and it is basically a sine omega t for t greater than equal to 0. T and omega are constant, and now you can write down sine omega t as 1 by 2j e to the power j omega t. See, two exponential. So Laplace of a sine omega t will be Since a by 2j will be common, it's a constant, it will come out, and then it will be, sorry, Laplace of e j omega t minus j omega t. So that will be a by 2j 0 to infinity e by j omega t st dt, right? So it will come out to be a by 2j. So from the first part, what you will get, alpha is here minus j omega, if you consider this case, minus alpha t. So alpha is equal to minus j omega. It will be 1 by s minus j omega, and this part it will be a by 2j, alpha is plus j omega, 1 by s. But on the same principle. So upon simplification, it will come out to be a omega s square plus omega square for a sin omega t. Similarly, it can be shown that Laplace transform of a cos omega t will be as s square plus omega square, right? So this is a some few very common functions that you normally use and their corresponding Laplace transforms, right? Let me check whether I've missed out on anything. Step, ramp, exponential function. Okay. If it requires, then it is, if it is required, I'll discuss other functions as well whenever it becomes necessary. Okay. Now let us move on to the next slide. Let us consider some typical cases. This so far we have considered some given functions. Now, what if there is a translation associated with the function? That is translated function. Now, what is meant by this translated function? Suppose a function is defined we have a function such as defined like this. Now, if I translate this function by an amount alpha, so that it now translates itself like this. So there is a moment alpha, and this is obviously the time axis. So this is ft, and this signal will be f of t minus alpha. But if I just write f of t minus alpha, it will also consider this function up to t equal to 0. But the function is only starting from t equal to alpha. So to make sure that any value before t equal to alpha is also 0, I need to multiply with this. Because what is the, by definition, u of t minus alpha, this u is unit step function, is 0 for all t less than alpha, equal to 1 for all t greater than equal to alpha. That's why even if f of t minus alpha may have some value before or in between 0 to alpha, it will be completely suppressed while multiplying by this function. So this is how you can translate sorry, translate a signal right from ft to f of t minus alpha. Right. Now let us find out what should be the Laplace transform of this translated signal. So that will be Laplace transform of f of t minus alpha u of t minus alpha. This is very common scenario, as we have already discussed in the last class. Like for the property of time invariance, we need to check that if we shift the input signal by amount capital T, the output signal, does it change its nature or it's just getting shifted by capital T? Then you call it a linear time invariant system. So for that, this kind of properties will be very necessary. So let us find out the corresponding Laplace transform. So that will be from 0 to infinity f of t minus alpha u of t minus alpha e to the power minus st dt. Now you can change the variable from t to capital T by, say, your capital T is equal to t minus alpha. So it will be equal to minus alpha to infinity. When t equal to 0, tau is equal to minus alpha. It will be f tau u tau, and this will be t is equal to tau plus alpha e to the power minus s tau plus alpha d tau. Now see, we have already considered that for any time t, ft is 0 for all t less than 0. So here also that should be valid for all t. So this will be also valid for tau. So we have to ensure that f tau u tau is 0 for all tau less than 0, which follows from this assumption. So the limit will now that you need to consider is only from 0 to infinity. So it will be 0 to infinity. And see, this u tau is nothing but 1. So you can write 0 to infinity f tau, and then we have e to the power minus s tau and e to the power minus s alpha d tau, right? Now, since this portion is independent of tau, we can get that out. So we can write simply, I'll just repeat the entire line. From that, you can write e to the power minus s alpha 0 to infinity f tau s tau d tau. So this is nothing but fs. So it will be equal to e to the power minus alpha s fs. So you can write Laplace transform of this translation t minus alpha with this. Okay. And that is true for all alpha greater than equal to 0. So whenever you have this translation type of a signal, f of t minus alpha, and you have to accompany it with u of t minus alpha to ensure that the causality condition is always followed. From causality conditions means here the axis or the origin has shifted from t equal to 0 to t equal to alpha, and before that there is no such signal available. Then you get very important properties. That's why I'm just recapitulating these things, and we'll be using this property throughout this course. Another function that we normally encounter is a pulse type function. How it is defined? Ft equal to a by, sorry, t0 for 0 less than t0, it has some value. t0 is a constant, and equal to 0 for right, where a and t0 are constant. So this is a typical uh, pulse function, right? So between, if we try to draw the corresponding nature of the pulse signal between 0 to t0, say if it is 0, so we have a signal like a by t0 between 0 to t0. This is the t0, and from t0 onwards, now the next question comes: how do we define such a pulse type of a signal? How do we define that? See, if you consider this pulse signal, how can we define this? Let us see. Let us consider first a step function, and obviously the magnitude is same, a by t0. So this signal, yellow signal, is f of t, or you can write this as f of, not like f of t, like say this, like what will be the signal? A by t0 ut. Now if I have another signal like this, which is said termed as a by t0 u of t minus t0, that means it's only starting from t equal to t0 and then goes like this. And if I subtract this blue signal from this, or if we write like this, a by t0 ut minus a by t0 u of t minus t0, then what you'll get? We'll get only this portion, nothing but ft. So you can write ft like this. You agree? So Laplace transform of ft will be Laplace transform of a by t0, which is a constant ut, minus Laplace transform of a by t0 u t minus t0. So that will be equal to a by t0 1 by s minus a by t0 into 1 by s e to the power minus s t0 because of this. So ultimately you can write this as a by t0 s 1 minus e to the power minus t0. So this is how we can calculate the Laplace transform of a pulse function, right? If we know this, that Laplace transform of a pulse function is this, can we find out the Laplace transform of a specific pulse function? That's the impulse function. What is impulse function? say gt is defined as a by t0 with limit 0 for 0 is equal to 0 for t less than 0 is for signal's causality, and it's like ideally time axis like this. So pulse function will be this, right? Something like this. And height, here we have considered the height of the pulse transfer function to be a by t0, and this width is considered to be t0 with the condition that t0 tends to 0, right? So this area, what will be the area under this impulse if we consider height by height into with thickness a. There's the area under the impulse function, right? So given this type of impulse function, if I tell you to find out the Laplace transform, what will be the Laplace transform of gt? That is limit t0 tends to 0. I've already found out the Laplace transform like this in generic form: a by t0s 1 minus e to the power minus s of t0. Now I have to use the dt0 of a, very standard practice of this. So if you couple this, it will come out to be 1 a. And there is a very specific kind of impulse function that is called a Dirac delta function, which is defined as delta for all t not equal to t0 and equal to infinity for t equal to t0 and minus infinity to infinity t to t0. It's a typical function, right? Direct delta function. And there's also another concept of unit impulse function that you might have heard. That unit impulse function means the area under the curve is 1. So that is means a equal to 1 is also there. Okay, so we'll come into these signals again when studying the transient response of a system. So this is very common function. Now I'm just giving you an idea of the Laplace transform. See, any function that is defined like this mathematical expressions can now be represented by a formulation, and then we have used algebraic formulation. Then we have used some standard procedure like translation and a pulse is a discontinuous function, a pulse function, an impulse function. Now, just like translation, there is another very important scenario that you normally face, that is multiplication of f by e to the power minus at. Then simply I'll just simply put out the result. It's very easy to follow. Infinity e to the power minus at ft minus st dt. As you can easily see, it will be s plus a minus s plus a. So it will simply become f of s plus alpha. Let's find out fs and replace s by s plus alpha. Okay. And common example, like we know that Laplace transform of sine omega t that already defined as omega by s square plus omega square. Say that if that is fs, then Laplace transform of e to the power minus at sine omega t will be f of s plus alpha. That means omega s plus alpha square omega square. Things like that. Okay. So this will find application of this while dealing with different physical systems, right? So these are the very common functions that we have to understand or recap to carry out our study of the Laplace transform. Now, moving on, there are some theorems based on the Laplace transform, and I'll also ask you just in any textbook. I'll also share a PDF where I've extracted that from a particular textbook, which you should go through, and there will be a list or a table of Laplace transform. That is common functions and their Laplace transform, and also common Laplace transformed function and their corresponding time domain equivalent via inverse Laplace transform. So you should go through it, and the very basic things that I'm discussing over here, so that you can understand, the table, or whenever you feel not sure, then you can derive that. Okay. Now, a very two very important theorems that you should understand. These two theorems are most important. In the sense, we will be using these theorems hmm, along with two other theorems. This is operational theorem, and there are some functional theorems in carrying out the study of linear dynamic system that is defined by ordinary differential equation. Now, what are these? First one is real differentiation theorem. That means we'll show that Laplace transform of ddt of ft, not ft, rather ddt of ft is defined as s of fs minus f0. That f0 is defined as initial value of ft, okay, at t equal to 0. And there is a notion that sometimes it is defined as t equal to 0 minus to indicate just before the input is applied at t equal to 0. In some books, you'll find it as t equal to 0 plus. Okay. So for notion, we shall consider f of 0 minus equal to f of 0 plus. That is just after the input is applied. And we shall represent them universally as f of 0. Right. Because there is a very conflicting notion that if you call f0 minus, some book they follow f0 minus, in some book they follow f0 plus. So f0 means at the time, at the very instant where the input is applied, what was the initial value of that function. Suppose we are dealing with a charging of a capacitor. Now the capacitor may be completely discharged, so the charge stored will be 0, or it may have some residual charge. So at t equal to 0, when you are applying the voltage, So you have to find out what is the charge present. If it is completely discharged at that particular instant before you switch on, then it will be zero. Or if you have some charge, then f0 will have some value. So it doesn't depend. F0 plus or f0 minus, they mean that without the effect of the charge, the external source or the input that you are applying, what was the residual amount present at that instant, right? Now there are certain examples where you can find out that it may be very conflicting, and one of the conflicts, I think I should clear this doubt, because some of you may have this conflict that when you have a signal like this, say a sinusoidal signal, in this case clearly f0 minus is this point. Similarly, f of 0 plus is this point, right? But that may not be true. In this case, this is true. But what about in this case? If you have a step function like this, so this is your f0 minus equal to 0, and say unit step f0 plus will be equal to say 1, because there is a discontinuity. Okay, so if otherwise not mentioned, whenever there is a discontinuity or discrete jump like a step function or things like that or pulse function, other than that, in every scenario this will be valid. But whenever there is a discontinuity at t equal to 0, in such cases what will happen, this function, this dft dt, if we calculate that at t equal to 0, what will be the function? It will be an impulse function, right? And therefore you cannot write f0 plus equal to f0 minus. Okay, so whenever there's a discontinuity at that instant, then this uh, equation must be modified. Okay, then you have to have two different parts. That is, one part will be, I'll just show the next page. One part will be Laplace plus, that is just after the discontinuity has occurred. So that will be SFS minus F0 plus, and another Laplace minus just before the discontinuity. It's a very typical case, because if I just write down this expression while calculating the Laplace transform of a function, step function with this ddt of ft, you might find it is very confusing. So just to clear this doubt, I have mentioned this. Okay, so this is this only confusion when there is a discontinuity. If there's a continuous function, then it's fine. Discontinuity, there's a step change like that. Okay, let us now prove this thing. So if given a step function is given, then you can obviously use either of them, but it is preferred that you use uh, for differentiation you use this function. Okay, or otherwise if it is mentioned, then you have to use follow that particular notion, either this or this if it is mentioned. Now coming back to the proof, what I have written, that Laplace transform of ddt of ft, yes, minus f0 in general. Now let us try to prove that. So if we take the left hand side, that is Laplace transform of ddt is ft equal to 0 to infinity. Uh, to write down this like t dt. Now I'll just prove this in another way. Now we'll take each part one at a time. So this is your ft. So normally what we can do, write down 0 to infinity any function ft e to the power minus st dt. What it will have two functions. Like ft is a function of time, your st is also a function of time, so it can be represented as just integration of this part. So e to the power minus st by minus s with limit 0 to infinity, and the next term will be 0 to infinity differentiation of this ft and e to the power minus st minus s dt. Okay. Now if we take Laplace transform of this, so we can simply write, so this is what, so this is one part, this is the other part. This part along with this part and this part, what they give Laplace transform of ddt of ft. So you can write down with a minus s, so plus s, so 1 by s Laplace transform of ddt of ft. Okay, and here we'll have only f0 by s, and this is what, this is Laplace transform of ft, that is fs. Okay. So from that, I'm just setting over here. From that, what you can write, take this over here. So multiplied by s. So we have Laplace transform of ddt of ft in right hand side is s fs minus f0. Right. Now, following the same principle, we can show that Laplace transform of the second derivative of ft, say this is Laplace transform of ddt of gt. So it will be s Laplace transform of gt minus g0. What is Laplace transform of gt? ddt of ft minus g0. So it will be s sfs minus f0 minus f10. What is f1? That means first derivative of f. So it will be Laplace transform of d2 dt square ft will be s square f minus f0 f10. Okay, followed? So in general, we can write Laplace transform of d to the power n will be equal to s to the power n fs minus s to the power n minus 1 f0 minus s to the power n minus f10, so on, n minus, sorry, s f to the power n minus 20 uh, and f n minus 10. Now this f of n minus 10, say just for a say, f n0 determines zero. Right? So this is the generic formula. Put any value of n. So this will be the generic formula for, and this is very important because in solving a differential equation, we'll see how this formula will come into our advantage. And let us, for an example, if we take a proof of this, suppose we have a function gt defined as for all t less than 0 and equal to cos omega t for all t greater than equal to 0. So if we show that the Laplace transform of this cosine function can be directly obtained, just like if in case of a sinusoidal function that you have done already. But what if we use the formula of real differentiation? Okay, then see how using the real differentiation formula of this we can find out this function, the Laplace of this. So for that, let us define another function f t equal to 0 for all t less than 0 and equal to sine of omega t for all t greater than equal to 0. So from this definition, you can write down Laplace transform of ft fs is equal to omega, right? Now we can obtain the Laplace transform of cosine function as Laplace transform of like this. So from that you can write down that 1 by s of fs minus f0. So what that will be? So that will be 1 by omega s into omega minus sine 0. What is sine 0? So it will be, this omega will cancel out. So s by s square plus omega square. So in any case, if we know the function, the Laplace transform function, then we can easily find out the corresponding Laplace transform of its derivative, and from that, that function can be obtained very easily. Now coming to the, and just as a continuation, I'll just mark this, that the formula for real integration. What is that? If you have a function ft defined as or not like that, that's simple like that. Laplace transform of integration 0 to t ft dt is fs by s. So let's prove that. So or it can be proved as well. Mm, sorry, how it can be proved, let us see. Laplace transform of integration 0 to t ft dt will be equal to what? 0 to infinity integration 0 to t f to dt s t dt, right? Then again you have two uh, different functions. So what I'll do, I'll take this integration, this portion as a function, and this portion as another function. So by rule of chain rule of integration, I'll do like this: integration 0 to t f t, sorry, dt, keeping that in constant. So by differentiating this, e to the power minus st by minus s from the limit 0 to infinity, minus differentiation of this thing. So this will be simply ft 0 to infinity ft, and this integration of this e to the power minus st by minus s dt. So what it will look like, it will be simply 1 by s integration ft dt at t equal to 0. That will be only left minus minus plus 1 by s 0 to infinity ft e to the power minus st dt. So this portion is simply fs. So plus 1 by s fs, and this portion gives 1 by s the integration of ft, which is calculated at t equal to 0, is normally referred to as f to the power minus 1 0. Okay, so f to the minus 1 0 by s. So I should also mention this. Okay. So that is Laplace of integration ft dt. So this term is something that you need to consider. What is this term? So the integration in time domain is how it is converted to s domain. If the initial value of the integral is 0, okay, that means if this value is obviously 0, then we'll only have this portion. Someone is trying to get admitted. Let's see him again. I'm going to say series. So if the initial value of the integration is 0, then it will be like this only. So and for the case that we have considered here, see, between the time 0 and t, okay, because it's a definite integral, okay, and if this ft is of an exponential order, then this Laplace transform of this definite integral will always have this ideal equal to 0. So this will constitute only this, and this ft should be of in exponential order. It's a function of exponential function, because in most of the scenario we'll be having only exponential functions to deal with. Okay, so these are the very common things that you need to understand so that you can solve the differential equations, and then we'll see how the inverse Laplace transform can be used in this regard. Okay, so first let us consider a differential equation and see how this differential equation can be converted into the Laplace seven. Oh, okay, another thing, a very important theorem that I've forgotten, that is much, in fact, very, very important, which is also very important for us, that is final value theorem and have you heard this final value theorem, initial value theorem? শুনেছো ফাইনাল ভ্যালু থিওরেম, ইনিশিয়াল ভ্যালু থিওরেম? এই রে, ঠিক আছে, আমরা দেখবো এটা কোথায় আমাদের কাজে লাগবে। হ্যাঁ, আমি একটু এখানে এগিয়ে যাই, তারপর এখানে ফিরে আসবো। আমি জাস্ট নোট করে রাখলাম। Okay, so let us see. Now, once we have obtained all this uh, recapitulation or the basic idea of the Laplace transform as a tool, let us find an example where we will be using this Laplace transform to solve a differential equation. Then we'll discuss what are the fine things that we need to, what are the key things that you need to remember. Then I'll recapitulate some of the ideas. For that, let us take an example. What is the example for? The example is on solving linear time invariant ordinary differential equations. Right? So let us take an example given x double dot t plus 2xt equal to 0. If we just mention this as a differential equation, this is not the complete information. So you also have to specify the initial conditions, which is the boundary value conditions of this. Where a and b are some constant. Now you have to solve this differential equation for this initial conditions, because we need the initial conditions, and obtain the corresponding expression for xt. So what will take? We will take Laplace transform of the both sides of the equation. So we'll have Laplace transform of x double dot t plus 3 Laplace transform of x dot t. We know Laplace transform of xt is equal to 0. We know because Laplace transform of f1t plus f2t is nothing but Laplace of f1t plus Laplace of f2t. Pretty standard practice. So from this x double dot t, what you can write? Sorry, x square xs minus s x0 minus x dot 0. For the second part, we'll have 3 s of xs minus x0, 2 of xs is equal to 0. Now, what are the value of x0 and x dot 0? Put those values. So, what we'll have? S square xs minus x0 is a, as minus b plus 3, sorry, sxs minus a plus 2x is equal to 0. Now, upon simplification, this will yield, just take xs terms, to as plus b plus 3. So the dependent variable that you want to calculate, you put that in the left hand side and now express or find an expression for the dependent variable xs as s plus b plus 3a by s square plus 3s plus 2. Now we need to solve this differential equation for different scenarios. Or we have to obtain from this xt by taking a inverse Laplace transform of xs. Now, to take the inverse Laplace transform of any such function xs, what we shall follow the method of partial fraction expansion. Right? Let us see how the partial fraction expansion can be used in this scenario to obtain the solution of xt from this. To obtain the inverse Laplace transform. So for that, we'll have three different scenarios: A, real and distinct poles. What are the poles? Poles means the roots of this polynomial. Then the next case, we'll have multiple poles or poles with multiplicity. And finally, we'll have complex conjugate poles. So discuss these three scenarios. Okay, so let us start with first case. If we have distinct poles, fs, say fs or xs involve distinct poles only. Then what we will do? So in this case, fs can be written as, say, bs by s, or some gain k I equal to 1 to m s plus zi divided by j equal to 1 to n s plus pi for m less than n. That means s plus z1 into s plus z2 up to s plus zm. In the denominator, we have s plus pi, s plus p1, s plus into s plus p2 into s plus pn up to s plus pn. So now this can be expanded in a partial fraction form like this: a1 by s plus p1, a2 by s plus p2, finally an by s plus pn, where this ak are constants and they are called the residues of the function at this pole s equal to minus p1, or residue of the residue at the pole s equal to minus pk, right? So this is how it can be expressed in this partial fraction form. The question comes, how can you calculate this individual a1 a2 up to n? For that, what you can do, you can simply multiply the fs by, say, s plus p1 into fs. So that will be a1 plus s plus p1 a2 s plus p2 s plus p1 n s plus pn. Now on this you apply s equal to minus p1. So what will happen? Each and every term will be 0. So this will come out to be a1. So in a nutshell, we can write that any value ak can be calculated as s plus pk into let's say fs, calculated at s equal to minus pk. So by this way, you can calculate each and every value of a1, a2 up to ak. Once we obtain that, so then finally you can write down fs as summation of I equal to j equal to 1 to n aj s plus pj. So taking inverse Laplace transform, then each and every factor will be like inverse Laplace transform of aj s, not j, say for any k, what it will look like? It will be ak constant e to the power minus pkt formula. So for each and every factor, we'll have expression like this. So it will be followed that from this you can write ft as that is a1 e to the power minus p for all t greater than equal to 0, right? So coming back to the example that we have been discussing, like this. Then you obtain the corresponding partial fraction expansion. What will be the corresponding partial fraction expansion for this? Now, how do you calculate the partial fraction expansion for this? So this can be represented as sorry as plus b plus 3a with the distinct poles s plus 1, s plus 2. So if we apply the same principle and if we express this as a1 by s plus 1, s plus 2, then you can find out a1 as s plus 1 into s plus b plus 3a by s plus 1 s plus 2 calculated at s equal to minus 1. What it will come up like? So this and this will cancel it out, minus 1 1. So 3a minus a 2a, so it will be 2a plus b. And what about a2? S plus 2 s plus p plus 3a divided by s plus 1 s plus 2 s equal to minus 2. So this and this gets cancelled out, so it will be minus 1, minus 2 plus 1 minus 1, minus 2a plus a plus 3a, so it will be a plus b. So the partial fraction will be for a1 2a plus b s plus 1 minus a plus b s plus 2. So what will be xt? Xt will be p e to the power minus t minus of a plus p e to the power minus 2t for all t greater than equal to 0. So this is how you can use this simple partial fraction expansion to obtain the solution of this differential equation, which doesn't involve any pole of multiplicity, or it involves only distinct is equal to minus 1 and is equal to minus 2. Right now what happens if we have a pole of multiplicity more than 1? That means sorry, sorry fs has pole or poles of multiplicity more than 1, or you can say multiple poles at a location in S plane, মানে একই পয়েন্টে মাল্টিপল পোল আছে। তাহলে আমরা সেক্ষেত্রে কি করে তা সলভ করব? তা সলভ করার জন্য একটা এক্সাম্পলই ধরে নিই ফার্স্টে। So your fs say has s square plus 2s plus 3 divided by s plus 1 whole cube. So since here I have pole of order 3 at s equal to minus 1, order 3 or multiplicity 3. So then we can write fs, and in this scenario fs will be written as b1 by s plus 1 plus b2 by s plus 1 whole square and now b1 b2 b3 are to be found out. So how we can find out? First, what you'll do, will multiply fs by s plus 1 whole cube. Then what you'll get? b1 s plus 1 whole square plus b2 s plus 1 plus b3. Calculate this at s equal to minus 1. So that, see clearly, all the terms will be vanishing and only will have b3. Next, take a differentiation on both sides of this equation. That is dds of s plus 1 whole cube fs. So what it will look like? b2, and from this side, okay, I don't get, let's not confuse, create confusion. So it will be two. Agreed? Now you calculate the same at s equal to minus 1. What you'll get? b2. Now again, take a differentiation. Another level of differentiation of this function. So if you take a differentiation, we'll get 2b1 and calculate that at s equal to minus 1. So you will get 2b1. So if we summarize this, what you can write, we can write down that b3 is s plus 1 whole cube fs calculated at s equal to minus 1. b2 is equal to dds of s minus 1. And finally, your b3 will be half. Why half? Because it was came out to be 2b3, right? Now let us try to calculate this, each and every one. So for b3, what you'll get, s plus 1 whole cube bs into s. So what you'll get is only the numerator. So s square plus 2s plus 3, right? Calculated at s equal to minus 1. So this will give you a value of 2. What about b2? We have to take differentiation of this. Minus 1. So that is this one, and that will be 0. And what about this? So this will be 1 by 2 d2 ds square of s square plus 2s plus 3 calculated at s equal to minus 1. That is 1 by 2 dds of this, that is half. Dds of is this is 2, that is equal to 1. So these are the three. So what we can write down? We can write down fs is equal to Oh, I've written both as B3. It should be B1. Sorry, B1. So your Fs is B1 by S plus 1. So what is B1? 1. 1 by S plus 1 plus B2 by S plus 1 whole square. So there'll be plus 2 by S plus 1 whole cube. Therefore, Ft will be Laplace inverse of 1 by S plus 1 plus Laplace inverse of L cube. It is 0, so I am not mentioning this. So this is equal to e to the power minus t plus cube means it is t square, and since it has a s plus 1 factor, so it will be e to the power minus t, or it will be 1 for all t greater than or equal to 0. So this is the final answer, ft. আর একটা ছোট্ট প্রবলেম করাবো, 2 মিনিট লাগবে। ঠিক আছে, এই কমপ্লেক্স ফ্রিকোয়েন্সি যেটা আছে, কমপ্লেক্স কনজুগেট ওটা বলি ছেড়ে দেবো, তাহলে শেষ হয়ে যাচ্ছে পুরোটা, বুঝেছো? আর এটা আমি পিডিএফটা দিয়ে দেবো। এটাতে if there is a fourth order multiplicity, then you have to calculate accordingly, fourth order ধরে করতে হবে। ঠিক আছে? আচ্ছা, s plus 1 to the power 4 থেকে শুরু হবে এবং ডিফারেন্সিয়েশনটা বাড়বে। আর এইখানে 2, বেসিক্যালি এটাকে 2 ফ্যাক্টোরিয়াল লেখা হয়, কারণ থার্ড অর্ডার উইল বি 3 ফ্যাক্টোরিয়াল, নট 2 followed by 3. It will be 3 factorial, then 4 factorial. It comes in a factorial form. হুম, এটা তো প্রমাণ করা যায় না, এটা একটুখানি মাথায় রাখতে হবে। যদি অর্ডার মোর দেন 3 হয়ে যায়, মাল্টিপ্লিসিটি অর্ডারটা। So now last, that if we have a complex conjugate pair of poles, then how do you calculate that? Oh, sorry. Okay. Now suppose given a system like this, I'm just writing just directly to the example চলে যাচ্ছি। fs দেওয়া আছে 5, তার মানে এর রুটস গুলো কোথায় আছে বলো? that is s square plus 2s plus 5 equal to 0. That implies, sorry, s plus 1 whole square plus 2 square equal to 0. So the factors will be s plus 1 plus j2, s plus 1 minus j2 equal to 0. Now the common practice is, if you now factorize this fs as a by s plus 1 j2 plus b by s plus 1 minus j2, it may be tempting, you may be tempted to follow like this, but I'll recommend you do not follow this method. This is not a very advisable method, because in that case you will have complex conjugate factors. This a and b will be rated as a is b conjugate, or the conjugate of a will be b, and vice versa. So how do you tackle such problems? First of all, what you can do, you write fs as 12 like this. Now you try to factorize the numerator such that you can follow this method. You have these two factors. One is sine function as a cosine function. So this can be represented at 10 plus, since there's a s plus 1 whole square, so I have to take into account that, right? So how it will look like? Then 5 into 2 divided by plus, right? So now if you take inverse Laplace ft, what you'll get? This is 5 omega by s plus 1 whole square omega square. So it will be sine omega t minus t, right? Similarly, this s by s square plus omega square. So it will be cos omega t, and this is s plus 1. So it will be minus t for all t greater than equal to 0. Right. See how easy it has been solved without going into the complications of getting the partial a1, a and b values and calculating the corresponding inverse Laplace transform. Ultimately, what will happen if you go on through this method? Finally, you will converge to the same answer. So whenever you find a complex conjugate pair of roots, you try to decompose it into as a combination of this type of factor, so that you can extract sine function and cosine function, a combination thereof, right? So this is where I will stop. So I just intentionally missed on or not discussed about initial value theorem and final value theorem, which is a very theorem regarding the Laplace transform. So in the next class, we're discussing the time response of a system. We shall discuss about initial value theorem and final value theorem. Okay. So in the next class, shall discuss about the time response characteristics. Fine. So yes, next Saturday. কেন বলো? ও আচ্ছা, 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 রাইট, গেটের এক্সাম। রাইট, রাইট। তাহলে তুমি বলো। Then we can reschedule that. We can reschedule that. I think 4th also there are gate for instrumentation. ইনস্টিটিউশন এ কেউ তো নেই এখানে। এনিওয়ে, হ্যাঁ, তোমাদের গেটের শিডিউলটা আমার জানার দরকার আছে। So it's up to you. If you want to skip next Saturday's class, then you can shift it to any other day. Maybe I am just you first আমাকে আমার সাথে কমিউনিকেট করো। ঠিক আছে? যে কখন কার সবার সময় হচ্ছে সেই বুঝে করব। হ্যাঁ? সেরকম হলে আমি আ কোনো স্যাটারডে সানডেও নিতে পারি। কোনো অসুবিধা নেই। ঠিক আছে? আমি এতে একটু কমিউনিকেট করে দিও ক্লাসরুমেই। একদম, একদম। ঠিক আছে? ওকে, থ্যাংক ইউ।